lecture number is 24th today, and we are going to discuss the use of current mirrors in differential amplifiers. This discussion had already started. We wanted this REE to be replaced by a current mirror because we could not use REE indefinitely in a lumped form because of two difficulties. One is difficulty of fabrication in integrated circuit, and the other is difficulty of increasing what? Supply voltage. The third difficulty, accompanying difficulty, is that if you increase the supply voltage, if you increase the resistance, then there would be consequent increase of dissipation also, and integrated circuits are not geared to dissipate a large amount of heat. So, the circuit that we had proposed was the following. The simple current mirror, capital R, let me draw this circuit again. This was Q2, this is the reference transistor, and then we have the second transistor where we want the current, and this resistance was RE. In the actual circuit of the differential amplifier, this is to go to minus VEE, and this is to go to plus VCC, and this is the current that I want. We call this I sub C1. This will actually be I sub, in the differential amplifier it would be I sub EE, okay, I sub EE. Now, this transistor is Q1, and our interest was to find out what is the effective resistance, effective REE offered by this transistor current mirror. We wanted to calculate this, and in the process we had taken some numerical values to illustrate the values, and this we shall require now. VCC was taken as 15, VEE was taken as 0. The current through the reference current was taken as 1.43 milliampere, which means that this resistance is equal to 10 K. 15 minus 0.7 divided by 10 K is 1.43 milliampere. I sub C1 we want it to be 50 microampere as an example. This is the level of current that is permitted in an integrated circuit differential amplifier. Then R sub E was calculated as 1.68 K with 50 microampere and 1.43 milliampere. RE was calculated as 1.6 K, and we had assumed that VA 12 was equal to 100 volt, and beta was assumed to be, I do not remember, maybe 100. We will see as we go ahead. 200? Alright, let us keep it at 100. I think we took it as 100. Beta was 100. Yeah. Okay, now we drew the equivalent circuit very carefully, and we saw that in the equivalent circuit the resistance that is offered by the left of the circuit was the parallel combination of R pi 2 and what else, capital R, R pi 2 capital R, then R 02 because from collector to emitter, and also that GM2 V pi 2 was equivalent to a resistance of 1 by GM2. This we had agreed to call R sub 1, small r sub 1, and we also argued that because IC1 is much less than IC2, R pi 1, which is proportional to, inversely proportional to IC1, must be very large compared to R pi 2, agreed, and therefore R1 is very small compared to R pi 1, and we could ignore it in the equivalent circuit. Is the logic clear? Because the R pi is inversely proportional to collector current, and the two collector currents are widely different, R pi 1 would be much larger compared to R pi 2, and R1 is smaller than R pi 2 because it is paralleled by a number of other resistors, and therefore the simplified equivalent circuit would be like this. We have E1 C1, between E1 and C1 we have GM1 V pi 1 and the inevitable R01. Now we cannot ignore R01 because that is what we are going to calculate, the effective output resistance offered. Okay. Then from C1, well, it is between C1 and the resistance is between C1 and what? Which terminal? E2. Between C1 and E2, between these 2 points, what is the effective resistance? So this is E2 and this is the impedance that we want to calculate. Between E1 and E2, E2 is the same as, no, between, I beg your pardon, this is not E1. Yeah, this is E1, C1 to E1, between E1 and E2, between E1 and ground there is a resistance of R, okay. And in addition from E1 R pi 1, because we have ignored R1, R1 is much less compared to R pi 1, and the potential difference is, which terminal is positive, lower one or upper one? Lower one. That is it. Okay. This is the equivalent circuit by ignoring R1. And to be able to calculate the effective impedance, what we do is we connect a voltage source V and find the current I. You see the expression can almost be obtained by inspection. As you can see, I is equal to, this current I is the same as the current flowing through this parallel combination, and this is minus V pi 1 minus, because the polarity is this, divided by R pi 1 parallel RE. And if we write the KVL, V would be equal to the drop in R01 plus the drop in RE parallel R pi. Therefore, V is I minus GM1 V pi 1, this is the current through R01 multiplied by R01, then minus V pi 1. Is that okay? The drop in this plus the drop in this, which is minus V pi 1. Therefore, you can eliminate V pi 1 from these two equations and obtain the value of effective R0. Effective R0, which is equal to V by I. A bit of algebra will give you the following expression: R01 plus R pi 1 parallel RE multiplied by 1 plus GM1 R01. This is what we get. Now one should notice that R pi 1 would be very large compared to RE. RE is only 1.68 K. What is R pi 1? R pi 1 is beta by GM, beta by GM. So beta by GM. What is GM? IC1 was assumed as 50 microampere divided by, let us say, 25 millivolt. This becomes 2 times 10 to the minus 3 mho. So beta is 100 divided by 2 times 10 to the minus 3 ohms, that is equal to 50 K. Agreed? So R pi 1, and what is RE? For the numerical example, it was 1.68 K. Therefore, R pi 1 is much greater than RE, which means that this quantity is approximately equal to RE. Okay. Now GM1 is this, What is R01? R01 is VA, which is 100 volt divided by I sub C1, which is 50 microampere. So this is equal to 2 meg. Okay, 2 times 10 to the 6. Therefore, GM1 R01 is very large compared to unity. In other words, this term can be ignored. Agreed? From a practical example, this term 1 can be ignored, and therefore my expression simplifies to a very simple one, and this is what is used for design. R0 becomes equal to R01 1 plus approximately GM1 RE. Let's take the the values that we have got now. If we calculate the values, this is 2 meg R01 we already calculated. 1 plus GM1 is 2 times 10 to the minus 3 multiplied by RE is 1.68 multiplied by 10 to the 3. That means this is equal to 2 times 1 plus, how much is this? 3.26, agreed? So many meg. 3.36. How could I make that mistake? Okay. So it is 4.36 multiplied by 2, 8.72 meg. Meg. Now, you see the advantage of using a current source. By using two transistors, identical transistors, which is of no concern in an integrated circuit, because you make thousands on a chip. There is no problem in making 2 extra transistors, and the resistors that you require, one of them was 10K and the other is 1.68K, which are both manageable within the precincts of integrated circuit. With that, the effective REE that you have got is 8.72 meg, and therefore CMRR would be twice GM RE. GM is 2 times 10 to the minus 3 multiplied by 8.72 times 10 to the 6. So how much does this become? Greater than 32,000. Okay, a very large CMRR, and this is why.
So
and
GM is the which transistor?
Okay, it's a good point. Actually, I have this has been used strongly. The actual value should be how much? Half of this. Why?
The current is coming from both.
Because IC1 is IEE, and therefore each transistor has half of this current. Each main transistor in the differential amplifier is half. Therefore, it would be 1 times 10 to the minus 3, and this would be 16,000. Even then, the figure is very large. I am glad you pointed it out.
Sir, could you please show the equivalent circuit once again?
Equivalent circuit once again. I will show you twice. All right. The question.
You have calculated connected R1 between E2 and E1. How have you done that?
That's right. R pi 1, I have to go back to the R pi 1 is between E2, this is E2, and E1. R pi 1 is from this point to this point, right, from base to emitter.
And so we have neglected I1.
Neglected, you see this resistance, the resistance looking here was approximately 0. Compared to R pi 1, this was negligible, and therefore it connected to ground. Is that okay?
Yeah.
Now I want to briefly recall the circuit. How this, I feel lazy to draw this again. I have this drawn here. Is this coming on the monitor? No, it's not coming. Okay. All right. So our circuit, how RE is used is like this. This is C. We'll draw it quickly. R sub C, R sub C. then we have the two main transistors Q1 and Q2. These are connected together. This is supposed to go to REE. Instead, what we do is we take it to a transistor, let us say Q4 RE. This goes to minus VEE. This is the main transistor of the current mirror and this is that Widlar resistance RE. And then from here we have the second transistor, which we call Q3 now, base connected to collector, and this terminal comes to the reference resistor, which was capital R 10K, the value that we used, and this goes to, where should this go to? This terminal. The bases are connected to the sources RS and whatever source VS1 and VS2. You see, what I wanted to show you is how R sub E is used. This is the circuit, that is R sub E. Okay, this pink colored outline, that gives you the equivalent of R sub E. Okay, small s, and I strongly suggest